Welcome to one of the most mind-bending mysteries in all of physics, the EPR Paradox and quantum nonlocality. Imagine two particles separated by vast distances, yet somehow instantly connected. Change one, and the other responds immediately, no matter how far apart they are. Let's start with Einstein's profound discomfort with quantum mechanics. Einstein strongly believed in local realism, the idea that objects have definite properties independent of observation, and that nothing can travel faster than light. The speed of light, 3 times 10 to the 8 meters per second, was supposed to be the cosmic speed limit. No information could travel faster. According to relativity, information between 2 points must travel at light speed or slower. But quantum mechanics seemed to violate this sacred principle. In 1935, Einstein, working with Podolsky and Rosen, discovered something deeply troubling about quantum mechanics. Let's understand the famous EPR thought experiment that challenged quantum theory. Imagine creating two particles in a special quantum state called entanglement. These particles are created together and share a mysterious connection. At the moment of creation, these two particles form a single quantum system, even though they're distinct objects. Now we separate these particles. Send one to Earth and one to Mars, or even to opposite sides of the galaxy. Separate them by distances so large that light would take years to travel between them. They're now completely isolated from each other, or so it seems. Now measure a property of particle A, say its spin. Quantum mechanics says before measurement the spin is undefined, existing in superposition. The entangled state is a superposition, 1 over square root of 2 times the sum of up-down and down-up states. Neither particle has a definite spin until measured. Here's the shocking part. The instant you measure particle A and find it spin up, particle B instantly becomes spin down, no matter the distance. Measure A as spin up, and instantly, across any distance, B becomes spin down. This correlation appears instantaneous, faster than light could possibly travel. Einstein found this completely unacceptable, and called it spooky action at a distance. Einstein famously called this spukhafte Fernwirkung, or spooky action at a distance. He refused to believe nature worked this way. Einstein argued there must be hidden variables, properties the particles carry from birth, that predetermine all measurement outcomes. Like twins carrying matching DNA, Einstein believed entangled particles carry hidden instructions that make their correlations seem mysterious, but are actually predetermined. So here's the question. Is Einstein right? Do hidden variables exist, making quantum mechanics incomplete? Or is nature truly non-local? In 1964, physicist John Bell discovered how to test this experimentally. Bell derived a mathematical inequality. If hidden variables exist and locality holds, experimental results must satisfy this inequality. This is a simplified form of Bell's inequality. E represents correlation between measurements at different angles A, B, and C. But quantum mechanics predicts violations of Bell's inequality. The correlations are too strong for any local hidden variable theory. Quantum mechanics predicts correlations equal to negative cosine of the angle between measurement settings. This functional form violates Bell's bound. Let's examine specific numerical predictions to see the violation clearly. At 0 degrees, perfect anti-correlation gives -1. At 22.5 degrees, -0.92. At 45 degrees, -0.71. These specific values violate Bell's inequality. So what did experiments actually find? Can we test Bell's inequality in the lab? The first experimental tests came in the 1970s and early 80s, led by physicists like Clauser and Aspect using entangled photons. A source creates entangled photon pairs. They fly to detectors on opposite sides, where their polarizations are measured at various angles. The result? Quantum mechanics was right. Bell's inequality was violated, exactly as quantum theory predicted. Experiments measured an S parameter of 2.7, well above the classical limit of 2. This clearly violates Bell's inequality. Modern experiments have closed every possible loophole. In 2015, 3 independent groups simultaneously achieved loophole-free Bell tests. Experimental precision has steadily improved over decades. By 2022, tests are so precise that local realism is ruled out with overwhelming statistical confidence. So what does this actually mean for our understanding of reality? First conclusion. Nature is fundamentally non-local. Quantum correlations exist that cannot be explained by any local theory. Crucially, this does not enable faster than light communication. You cannot use entanglement to send messages. Even though the particles are correlated, the individual measurement results appear random. You cannot control what you measure, so no information can be transmitted. You might ask, how can something be non-local yet not allow signaling? This seems contradictory. The answer lies in randomness. The correlations are perfect, but each individual measurement is completely random. You only see the correlation when comparing notes later. Let's dive deeper into the mathematical structure of entanglement. This is a singlet state, 1 over root 2 times the state 0, 1 minus 1, 0. It's the maximally entangled state of 2 qubits. Crucially, this state cannot be factored as a product of individual particle states. This non-separability is the essence of entanglement. We cannot write psi as a tensor product of separate states for A and B. The particles have no independent existence. When you measure particle A, the entire two-particle wave function collapses, instantly determining the state of particle B. Before measurement, we have a superposition. After measuring A, the state collapses to either 0, 1 or 1, 0, a definite state for both particles. Let's quantify exactly how strong these quantum correlations are. The correlation function C of theta equals the expectation value of the product of measurements A and B at angle theta. For entangled photons measured through polarizers at relative angle theta, quantum mechanics gives a specific prediction. The quantum correlation is negative cosine of twice theta. This gives the characteristic quantum oscillation. This graph shows the quantum correlation as a smooth cosine curve, regularly exceeding the classical bound shown by the dashed line. The maximum violation of classical bounds occurs at 22.5 degrees, where quantum correlations reach about 0.85 compared to the classical limit of 0.5. The quantum to classical ratio is about 1.7 at optimal angles, showing correlations 70% stronger than any classical theory allows. One of the most stunning features is that these correlations don't weaken with distance. Experiments have demonstrated perfect quantum correlations at distances of 144 kilometers between ground stations and satellites. The correlation C of D equals the initial correlation for all distances d. Distance simply doesn't matter. Whether the particles are 1 meter apart or 1 kilometer apart, the correlation strength remains identical. This is truly bizarre. In principle, this should work across the entire observable universe. Two particles entangled at the Big Bang could still be correlated today. But before we get too excited, there are serious practical challenges. The biggest challenge is decoherence. Any interaction with the environment tends to destroy the delicate quantum correlations. The coherence time decays exponentially with time constant t. The entanglement literally evaporates into the environment. The entangled system is bombarded by environmental photons, molecules, and fields, each interaction eroding the quantum state. In practice, coherence times range from microseconds in warm systems to seconds in the best cryogenic setups. To maintain quantum effects, we need incredible isolation from the environment, which becomes harder over longer distances and times. Despite challenges, quantum entanglement is enabling revolutionary technologies. Quantum key distribution uses entanglement to create unhackable communication channels. Any eavesdropping attempt is instantly detectable. Alice and Bob share entangled particles. If Eve tries to intercept and measure them, she inevitably disturbs the quantum state, revealing her presence. Quantum teleportation uses entanglement to transfer quantum states between distant locations without the particle itself traveling. Quantum computers exploit entanglement to process information in ways impossible for classical computers, offering exponential speedups for certain problems. The EPR paradox forces us to reconsider the nature of reality. The Copenhagen interpretation says measurement creates reality. Before observation, particles exist in indefinite superposition states. The mini-world's interpretation says all possible outcomes actually occur, each in a separate branch of reality. Bohmian mechanics, or pilot wave theory, restores determinism through non-local hidden variables that guide particles. Multiple interpretations attempt to make sense of quantum mechanics, but experiments cannot yet distinguish between them. The question remains open. All interpretations make identical experimental predictions. They differ only in the philosophical meaning they assign to the mathematics. The EPR paradox has profound implications for philosophy and our view of reality. Bell's theorem forces us to abandon either locality, the idea that distant objects cannot instantly affect each other, or realism, the idea that objects have definite properties. We cannot have both locality and realism. Nature forces us to give up one of these deeply intuitive notions about how reality works. So which should we give up? Most physicists abandon realism, accepting that properties don't exist before measurement. This preserves Einstein's relativity by keeping locality, but at the cost of accepting that reality is observer-dependent. The role of observation and consciousness in quantum mechanics remains deeply mysterious and hotly debated. Recent years have seen remarkable experimental and theoretical progress. The 2022 Nobel Prize in Physics was awarded to Aspect, Clauser, and Zeilinger for their groundbreaking experiments on entanglement. China's Mikia satellite has demonstrated quantum entanglement distribution over thousands of kilometers through space. A satellite distributes entangled photons to multiple ground stations simultaneously, creating a global quantum network. Researchers have observed quantum entanglement in increasingly large molecules and found hints of quantum effects in biological systems like photosynthesis. Despite enormous progress, deep mysteries remain unsolved. The mechanism of wave function collapse remains completely mysterious. What physical process causes superposition to become definite? We don't know if there are fundamental limits to how far or how large systems can remain entangled. Reconciling quantum mechanics with general relativity remains the holy grail of theoretical physics. Quantum mechanics and general relativity both work perfectly in their domains, but resist unification into a single coherent theory. Perhaps most mysteriously, we still don't understand what role, if any, consciousness plays in quantum measurement. Let's summarize what we've learned about this enduring mystery. The EPR paradox reveals that quantum mechanics is fundamentally non-local, with correlations that defy classical explanation. Bell's theorem proves mathematically that no local hidden variable theory can reproduce quantum predictions. Decades of increasingly sophisticated experiments have consistently confirmed quantum mechanics over local realism. Reality is even stranger than Einstein imagined. Particles can be instantaneously correlated across any distance. Yet Einstein was partly right. No faster-than-light communication is possible, preserving causality. Entanglement remains one of the deepest and most beautiful mysteries in all of physics, challenging our most basic notions about the nature of reality. The universe is quantum at its core, with non-local correlations woven into the fabric of reality.